Good morning, everybody. First of all, I would like to thank Amparo for the kind invitation. Today, I would like actually to talk a little bit about online machine learning or basically dealing with streaming data. So basically, my name, as you see, is Hamid Bouchachia. I'm from the University of Bournemouth. I'm leading actually machine intelligence group at the Department of Computing Informatics. What I'm going to try to do actually, I have many slides containing formal things and so on. I will keep the presentation a little bit short. So this is basically the outline of this presentation. I will introduce what data streams mean. Then I will talk in particular about competitive online learning. I will try to summarize more or less this section because it contains a lot of stuff. Online active learning. Then I move on to distributed online learning. I have some open questions, but then I would like actually to introduce the Horizon 2020 project what use, which is related actually to this area of learning from data stream, and that somehow already introduced. Okay. So basically, when you look actually at the nowadays environment, you will see actually a lot of applications where the data is coming in the form of stream. The problem there is of course sometimes the data is coming from non-stationary source, which means that the data is you cannot actually know much about actually the source or emitting the data. So data stream is a high-speed continuous flow. So the characteristics of data stream, as you may imagine, so usually we think actually about data stream as infinite. It means it is unbounded, and as you see, also it can be non-stationary, so meaning coming from non-stationary environments, so we don't assume that we have the same statistical characteristics all the time. And of course, sometimes if you are dealing with some environment where you need to control, for instance, plants or let's say just this amphitheater, if you have sensors, implanted everywhere, and you would like actually to control, for instance, the comfort of this room, then of course you have to do it quickly, you have to react quickly. And this is a very typical characteristic when you want actually to do control based on data streams. So this is basically what you expect. So you have actually multivariate stream, and you need actually to build some machineries, call it just computational algorithms, that allows you actually to infer from the data to make decisions in real time. But because you don't have, at a given time, you don't have access to the full data, yeah? So your algorithm should actually use more or less approximation, and the outcome should be rather approximate result. Of course, in some situations, if the algorithm is very efficient, you may get really accurate results. Okay, and the intention, of course, is to build a model that can self-adapt over time. It means as data comes in, your model can be adapted to the new data. So the requirement, as you may, there is just mismatch between PowerPoint and LibreOffice. So that's why you see this shift. So we have actually the first thing is to build models, and we have actually to choose between two approaches. So you have evolutionary approach against versus revolutionary. In evolutionary, you want actually to learn from the data as it becomes available. And your system can be, in a sense, incremental, okay? While revolutionary, if the data, because we are talking about non-stationary resources generating such data, if you see that there is a drift in your data or your system is not able actually to generate good results, then you may retrain your model, okay? So you have flow of data, stream of data. If you detect that there is something wrong with your system, then you cancel simply that version, and then you start training a new model, okay? So these are the two ways actually of dealing with streams. So either you build quite smart algorithm that self-adapt, or you need actually some mechanism to detect that your algorithm is not doing well, and you need actually to retrain it based on the new data, okay? Then we have actually another decision to make is related to memory. So we have no memory paradigm and partial memory. I will come to this anyway a bit later. So no memory means that your algorithm shouldn't store any data, any piece of data. Once it processes a data point, it throws it away. Okay? While partial memory, you may think if your data is cyclic or it presents some phenomena that you master and you need actually to capture those phenomena throughout the time, then you may select some representative data points, yeah, and those are called partial memory. So the algorithm at the end of the day will consist of the model, yeah, the algorithm, as well as a subset of data, sample of data that is required actually to reflect on the data stream or the nature of the data stream. And then one thing which is very, very challenging, of course, is low computational time. I mean, usually in online learning or when you are dealing with streaming data, you need to have very efficient algorithms. So the complexity has to be linear or sublinear in the worst case, because we were talking already about real-time processing, yeah, because data is sampled at higher probably sampling rate, and you have to process it quickly. So if your algorithm is slow, then it is not going to cope with the data, with the stream. And therefore, your algorithm has to be really efficient in terms of processing, okay? And I'll come to this later on when I start actually talking about distributed online learning. So you can imagine actually that data streams are everywhere. I look at this list actually of applications, web data, sensor networks, plant control, financial data, and so on. All these applications really basically are based on data streams. And what you see here on the picture is ArcelorMittal plant, which is involved actually in this Proteus project, and we would like actually to do more or less some analysis of the data stream generated by a set of sensors that control the production of coil. So we could distinguish actually two classes of algorithms that are dedicated to data streams, namely sketches, and then we have typical machine learning algorithms. So for sketches, we are rather talking about statistical moments, statistical characteristics like frequent item sets, like distinct items, like moving average, variance, moment 3, moment 4, and so on. So those are simply, routines that algorithm could use. So there are plenty actually of work in this area of sketches. And what it means actually sketch is that you want actually to use one data structure to basically compute some statistical quantities, in real time. So they are updated in real time, okay? And then we have the standard algorithms, which could fall in any area: clustering, classification, regression, feature selection, reduction, and so on and so forth. So we have these basically two classes of algorithms that we could investigate in the context of data streaming. So just actually to make the point, the difference between batch learning and online learning, it's worth probably to say some words about batch learning. So when we do basically learning, well, we assume we have a data set, that is supposed actually to be representative. So it has to cover actually the full space. When I say space, feature space, okay? So that if you train a model on it, you are sure that you are capturing the phenomenon that you are trying to learn, okay? So the data is supposed to be representative, okay? And the size might be moderate, unless you use actually big data platforms, which are quite recent technologies. And the thing which is specific actually about the batch learning is that you can cycle over the data, So you start your learning, using different actually a number of epochs, So the algorithm can see the data more and more and more. That's cycling, okay? And then the computation complexity, we don't care too much about it actually in batch learning because simply the learning is done offline, okay? So it depends really on the algorithm. Some of the algorithm could be linear, some others could be really even greater than quasi-linear complexity. So the problem with this is that we cannot actually use it for streaming, because simply, by definition, streaming is big data in the sense that you have actually continuous flow of data, so you cannot, by definition, store all the data so that the algorithm can see it again and again, okay? So batch learning cannot be really used in streaming unless, as we said before, you opt actually for the revolutionary approach. And in this case, you may use offline algorithm which you retrain on batches of data, on recent data, of course. Okay, and in online learning, basically, what we would like to do is to develop algorithms that can see the data only once. So you see one data point, you process it, and you throw it away. Okay? So all data is never used in subsequent stages. And one thing actually which is quite standard or interesting actually in this area of online learning is we have this paradigm or trade-off between plasticity and stability. So plasticity is about learning knowledge from new data. So your system is plastic, means it can always learn. yeah? And then you have stability. You would like to avoid that your system basically forgets, okay? And you may try actually to, to have a balance between these two things. And it's there where we need really to devise a quite efficient algorithm. So we would like to learn from data without forgetting what we learned previously. And then the other interesting aspect in online learning is that you are not supposed to know anything about the data. So the data changes over time. And even if you collect some statistics, at some time they will not be valid because the data will change, okay? And your algorithm need not actually just actually to update basically probably the model in terms of parameters, but also it has sometimes to change even the structure, okay? And this is very, very important. In offline, of course, you do cross-validation or whatever technique to fit your model. So in online, we have actually to find similar mechanism to do that in real time. So online learning, very in a simple way, given actually a sequence of input, you would like actually to refine the hypothesis, and the hypothesis here is simply the algorithm, the model. Okay? What you want to do is, of course, you would like actually that the hypothesis at time t depends only on the current input, yeah, in the stream, as well as the current hypothesis, because we said that the algorithm should not look actually in the past, cannot use actually data or old data. Okay, so this is that why actually offline, or online is faster than offline learning. The interesting thing also is that you can query your system. You can use it to predict any time, because this is open-ended algorithm, open-ended system. So the system learns, at the same time you can use it for predicting. So there is no separation between training and deploying. That's in offline, you need actually to have two phases or three. So you have the training, you have the validation, and you have the deployment, or you call it testing. Okay? So in online, you have all these merged together in one model. Okay? So the challenges with streaming is, of course, because the data can come actually from a non-stationary resource, it might suffer actually what we call concept drift and novelty. So concept drift, it means that the data will drift from the region in the space where originally it was stemming from. Okay, so if you build your model on let's say in 1 hour, okay, assuming that the data is coming from a particular space, okay, so if the data changes, then your model will not be able actually to work. Or if you in offline, usually you assume actually that you know, for instance, the number of classes or whatever. In streaming, sometimes you don't know. You don't know the number of classes. Sometimes in a plant, of course you know that you have two behavior. One normal behavior where everything looks fine and so on, and then you have abnormal behavior where something goes wrong. But still, you don't know actually the different types actually of faults. And that's basically one typical example where novelty detection is very important aspect. So you assume that you can learn new classes as they emerge. Okay, that's not the case actually in offline. Okay, this is basically just summary, just to make it clear. So model learning here, relearning, or if you want, this is the revolutionary approach. So you learn model from examples, you store the model, you store the examples as well, yeah, and then you use the model to predict. If you have new examples, then you add them to the current example, and then you retrain your model. Okay? Now, if you go for semi-incremental or semi-online, I don't need to go into this discussion, the difference between incremental and learning. So you learn the model from example, you store the model, you store some representative examples, and then you can use your model to predict. When new examples arrive, add this to the current examples, and then go to step 1 to adjust your model. In online learning, the story is a bit different. So you learn the model from examples, you store the model, and you discard the examples. Okay? And then you can use actually your model to predict, and when new examples arrive, all you do is just to learn further from these examples, and then you discard them. Okay? So that's basically a summary of the whole. So now I'm moving actually to a bit to the theoretical basis for online learning. So we have this protocol, which is adapted actually to classification and regression in particular. So, I mean, this is typical. Of course, you can adjust steps in it, but this is the standard protocol. So the learner, I mean, if your model, your algorithm receives a data point xt, at time t, it receives an input. Now the learner makes prediction. It doesn't process the data. This is part of the learning. It predicts the label or the corresponding output for your input, okay? And you call it actually y hat, okay? And then the nature, yeah, the environment, basically shows the ground truth. So the learner receives the ground truth, and then the learner incurs a loss. And the loss here is simply the discrepancy between the output, the ground truth, and the predicted one, okay? And updates its hypothesis. So you do prediction first, and then you update your model. So one point actually that sometimes very difficult actually to fulfill is we would like actually to develop algorithms that are lossless. And lossless, it means if you develop the algorithm, you adapt actually the algorithm to operate on data streams, ideally it has actually to have the same performance as if you develop the same algorithm to operate offline. So because you do a lot of approximations for online, it's quite challenging to produce actually lossless algorithms. Okay, so there is always a trade-off between the performance, of course, the processing of data and the quality of the output. Okay, everything has changed now. Okay, so. The area actually that we are trying to work on is called competitive online learning. Of course, we work on online learning in general, But today I'm going actually just to show some work that we did actually in this area of competitive online learning. So that's basically exactly the protocol that we were talking about. So you receive feature vector X, you predict the label Y hat, and then you receive the true outcome Y, and then you suffer the loss. So there are actually, this competitive online learning dates actually to the 80s, 90s. And one paradigm which has been very, very well explored called learning with expert advice. And there were many actually algorithms. You have the halving algorithm and you have online weighted majority voting, two versions of it. And for the halving algorithm, here, if we assume that we have an expert, and one perfect, I think there is a mistake in then at most log n mistakes can be made. I mean, when you are predicting, the perfect expert can make at most log n, where n is the number of experts. For online weighted majority voting, what we try actually to do, I'm sorry because here I see that the mathematical symbols have changed because of the incompatibility. So if we assume that the best expert, if you have a set actually of experts, that's I should have said it here. So when we talk actually about the learner here, you might have actually a number of experts that predict, and then there is one learner that combine the output produced by the experts. So it's just generalization when we work with experts. Now, for the online weighted majority voting, if the best expert among all makes opt, that's the number actually of mistakes, then the number of mistakes that can be made by the learner is going to be basically less or equal a number 2.4 times the number of mistakes made by the best expert plus log n, okay, where n is the number of experts. So this is, while doing the prediction, this is what we call the bound. So you are sure that the number of mistakes that your algorithm, your online algorithm, is not going to exceed, to go far beyond this limit. So the idea of basically learning with expert advice is to use a set of experts, making sure that the learner, your algorithm, should perform as good as the best expert. So that's the bound has to be, the bound has to be close to, or the number of mistakes that the learner can make should be close to the best expert. Now, there are, of course, different versions with different, actually, bounds. Here you have actually randomized. It comes actually with a different bound. And here what we tried actually to do is to use online regression using a particular algorithm based basically on this protocol we mentioned here, which is called the aggregation algorithm, okay? So it's, again, prediction with expert advice. So you assume, actually, that you have a set of experts, theta, coming from a set of experts. Each predicts a certain output, and then the learner, so the aggregation, will basically output, using the individual output from the experts, output a certain prediction, which is gamma t. And then the nature outputs the real outcome, okay? And then now we should compare basically the outcome of the learner against the ground truth, as we mentioned before, yeah? And then we could basically adjust the learner and the experts based on the loss of them. Okay, so this is basically the algorithm. Now basically the loss of the learner is basically just the sum of the losses of the algorithm of the experts, yeah. While the loss of an expert is local. So it just whatever actually loss function you use, it depends actually on, because this is stemming actually from more or less inspired from game theory. So the loss of the learner is just the sum of the losses. So here, if you think about it in a way, this is kind of game. When you look at the protocol here, you do prediction, and then there is somebody to tell you this is the ground truth, and then you try actually to adjust your model based on that output. Okay, so sometimes it's adversarial, meaning that you say something, and there is somebody else to try really to contradict you, and then you have actually to learn the strategy, how you generate actually the output from this game. Okay, so the interesting thing actually about this aggregation algorithm is that its loss is less or equal the loss of the best expert plus more or less a constant, which is log n divided by eta. So this is very, very strong bound. So whatever you do, you are sure actually that your loss is not going to be very dramatic. So it's going to be close to the loss of the best expert. So this is the aggregation algorithm. I'm not going to go into details, but this is what we try to do is to use basically this aggregation algorithm for regression purposes. And we had actually to use online ARMA because we are dealing with streaming. The point here actually is algorithm 2. It's basically ARMA. Probably you know. This is the expression of ARMA is on algorithm 1. And this is formulation, actually, online formulation of the ARMA. And so the idea here is to predict basically the next value in your time series, yeah, using basically the predictions, as you see here. Value in your time series. So you predict the value, that's the xt phi theta, and then you observe the real one, and then you suffer, and then you update actually using the stochastic gradient descent. So this is, of course, amenable to distributed systems. If you are using stochastic or online gradient descent, then it has been proven actually that the algorithm can converge. Okay, so we use actually ARMA as experts. Okay, as you see here, we use actually 2 time series here, temperature, and we use basically ARMA 2.2, which has been tested offline to find really the best model, and then we tried actually to compare a number of experts. So, I mean, this algorithm comes with 2 parameters, namely M plus K, as you see here. Yeah. So that's basically the number of points points that you are going to consider and correspond basically to the number of experts. Okay, so the interesting thing here is that we found out actually that the combination of this aggregation algorithm with the online ARMA model provides quite very good results, as you see here in row 5. Okay, so the benchmark which we trained actually offline is of course the best, but AA, plus ARMA, stochastic gradient descent, is far better actually than the best batch, or the second version is using basically AA on batch learning, and BO is the best online learner. Okay, so it's quite competitive. So here we see that in such context, online learning provides really very competitive results against standard offline learning. Okay, so this is another experiment. This is basically part of the Proteus project. So we are trying to predict the quality of the coil during the prediction using a number of sensors. So it's around 7,800 sensors or so. So we built actually this model for this purpose. Okay, so to predict the quality, which is the flatness of the coil, yeah, based on what we call Flattest Map. Now, we also developed a new algorithm, which is basically similar to the previous one. Just here, instead of using ARMA, which operates on one feature, Lasso is, which stands actually for least absolute shrinkage and selection operator. So this is the formulation here, beta Lasso. It's the standard, basically the least square, yeah, plus penalty on the parameters. And here we use actually the L1 optimization. What is interesting actually about Lasso is, of course, it does two things. It does regression, but also it does feature selection. So if you have a huge feature space, yeah, then it is really something very good to consider, okay? The problem is that if you are operating in online, there is no online version of Lasso. So that's basically what we developed here in this algorithm, as you see here. We proved also the bounds of this algorithm, okay? So that's basically the algorithm that can basically handle, the prediction as well as the feature selection. Okay. So AA is basically embedded in the algorithm. What you could think actually about this is that each feature could be considered as expert. And you want actually to find the relationship, between features and the output. And in this case, if you consider actually each feature as an expert, you would like actually to track how strong each expert. And AA, what AA does, it allows, let me just go back to AA, just to make sure that we are talking about. So here, if you look at the last line here, here we are actually assigning weights to each expert. And in Lasso, if you assign an expert to each feature, then each feature will have a weight. And therefore, this weight can be eventually cancelled, can be zero. And therefore, the feature will not very important actually for the prediction. So basically, again, here we compare the Lasso-based regression using AA, the last line here in this table, and you will see actually that it is quite good algorithm compared to standard regression algorithms. So this algorithm actually we developed again for the purpose of this steel industry application. We had actually a very challenging requirement from the partner, industrial partner. So the idea was actually to be able to predict the quality of the coil during production, which means that when the coil is passing, let me just show you the picture here so that you appreciate the difficulty actually of this scenario. So here when the coil is being produced and moving actually along the production process, you have actually sensors capturing data, okay? So it's stream. And they wanted basically to predict the quality of the coil before the production stops. I mean, before the coil has finished. Okay? So we had actually to develop quite efficient algorithm that help us actually to predict the quality of the coil as we get more data before the end, because they want actually to stop the production or to change, for instance, the temperature, the speed, the tension. They have a lot of parameters before this coils or before the next coil gets into production. So we had actually, it's very constrained actually application. So these are basically the things that we had actually to consider. So the algorithm receives all the streaming data from all sensors and then predicts. That's if you want actually to predict the quality of the coil at the end of the production. So you assume that you have the whole sensory data, okay, and you are going to predict. That's scenario one. Scenario two, if the algorithm receives just part of the data, yeah, from all sensors, yeah, and you would like to do the prediction. Scenario two. Scenario three, the algorithm receives all data from new sensors and predicts. Okay? All data, but just from few sensors. And then the last scenario is that the algorithm receives just part of the data, and unfortunately not from all sensors, and you have to make prediction. So the scenario was quite challenging, and Lasso was basically tested on this, and it does quite well, really, with all these scenarios. Now I'm going to move actually to a second actually block of this this lecture. And I'm going to talk actually about online active learning. So what is active learning? Still we are dealing with streaming, so that's always streaming. So if you think actually about classification and clustering, then these are supposed actually to sit at the end of spectrum. So if you have labels of data, then we are talking about classification. If you don't have labels of the data, then it is the case of clustering. But in the middle, there are plenty of things. There are plenty of scenarios. So we have what we call learning with partial supervision. So in this case, you assume that you have few data points that come with labels, and the majority of the data is not labeled. And you would like actually to train a model that uses all knowledge that you have. And you would like actually to use also the unlabeled data when you are using classifier, or you want to use labeled data when developing a clustering algorithm. Active learning is about basically a kind of learning with partial supervision, but here there is a user who can basically tell you this is the label of these data points in real time while you are training your model, okay? So active learning is supervised learning in which the learner is deemed to choose as few unlabeled data points as possible, request their labels, and use them actually to update the model. So the point here is, of course, you want to increase the accuracy of the learner, but you would like, not to overload the user who is providing you with the labels. So you would like to pick as few as possible, few data points as possible. So this is what you could imagine. So you have a pool of unlabeled data, and you may have actually two ways of using this unlabeled data. Either you use active learning and you try actually to ask the user actually to label for you few data points chosen by the algorithm that you use, or you use selective sampling, and this is non-supervised, so you just actually use probably clustering. You say, okay, all data that are close to some centers or centers of the cluster can be used actually to train a model. Okay, so at the end of the day, you would like actually to use what exists as labeled data, yeah, so originally labeled data, and data points that have been labeled either actively by a human in the loop or using clustering or any other mechanism, okay? There are different actually approaches to do active learning. So active learning is the process of selecting very specific data points that can be labeled to train your model. Okay, so that's the definition in few words. So the approaches to do active learning, so we have a number of approaches. You have membership query synthesis, you have pool-based selecting sampling, but we are rather interested in this, which is quite new, called stream-based selective sampling. So you have a stream coming, and you would like actually to build a classifier, for instance, okay, where basically you don't have a lot of labeled data, because by nature this is a stream. So there is nobody actually able actually to give you labels every now and then. But in the case, for instance, of this steel industry case, we had actually regression problem. So the system that produces the coil has also an inspection system using camera that computes some quality values of the coil. So we had basically we didn't basically need any active learning. We had different problems. I might mention later on. So, but this is the case. You would like actually to choose some of the data points and use them. Ask actually a user to label them and use them for training your model. So here we could distinguish actually two mechanisms for choosing data that can be labeled, actively labeled by a user, namely label uncertainty. If you look at the figure below here, we would like basically to select those data points that are close to the boundary and ask the user actually to provide the user the label. We are not interested in these ones which are far away from the boundary. We would like basically to ask only about those that are close to the boundary. Okay? So that in a way to minimize basically the labeling effort. Then we have the density base. Sometimes we would like to select representative data from some clusters. So in this case, we need clustering mechanism to generate for us dense regions, and then we could select basically some data points from there, and we ask the user to label them in order actually to build our classifier. So when you want actually to use this active learning, you have actually to decide basically which criteria you want to use to make decision about which data points you want to label, okay? And there are actually two main approaches to do that. So one is based on decision theory based, which you would like actually to use to select your query data. And then you have information theory based. The first one looks at the prediction error. So we would like basically to choose the data points that lead to the lowest expected future error. So that's one way of doing. The second way is that you would like actually to be very generic, and you would like actually to look at the model parameters. So you want to query the data that leads to the highest information gain, okay? So from information theory. So we basically provided a number of algorithms following different paradigms. So the first one, for instance, we published it already in algebraic transaction on your networks, which basically deal with the first one, which is the expected future error. And the second was, the second one, well, I will come to it anyway. I'll come to this because I would like to explain first this problem. So what we want here, basically, in presence of data stream case, is that there is always a risk that your data drifts. It means that the model that you build in early stages does not fit anymore because the data has changed the distribution. And what you want basically your active learning algorithm to cope with this problem of drift, okay? So for instance, here incremental, you have actually the data emerging in a certain way. Or a new cluster actually that comes at the end for instance, at one extreme of the space. You may have also actually sudden or abrupt drift when suddenly you have new emerging regions, and in this case. Sometimes it's easy actually to cope with it compared to incremental. Incremental, you have really to track the change, while abrupt, it can be easily captured. But there are other different types of drift where the data changes in a cyclic way. For instance, here recurring concepts. If you are, let's say, tracking the temperature in the room. You have 4 seasons, you have summer, you have winter, you have autumn, you have spring, and the temperature will change actually based on the season. And you would like actually to build, for instance, a model that takes this into account if you were actually to, I don't know, to control the heater in a room, okay? So what we said actually is that we developed some decision-based active learning using basically the prediction error. So we would like actually to find the data point that allows to minimize the expected future error. And as you will see, I'm not going too much into the details, but if you try actually to model this risk, I mean, this is the last one here, you would like actually to predict basically the joint probability of input and the output given the set of labeled point and the full data labeled and unlabeled. So because we are talking about active learning, so we have some data points labeled, some others not labeled. Well, you can develop actually this, and your model at the end of the day will look actually as a combination of two things, classification and clustering. And that's exactly what we mean by semi-supervised or active learning, is that you have data that is labeled and you have data that is not labeled. And what we wanted also actually, if you remember, is to have these two things, label uncertainty, which is related to the classification, because we look at the points that are close to the boundary. And we said the second criterion is the density. So that's related to clustering. Now the development that we did, allow us actually exactly to express those two criteria. So you have the classification, that's basically label uncertainty, and then you have clustering, which is related to density-based labeling. Okay, so this is the way we can visualize this. So if you use just the density criterion, then you are going to select data points just from some clusters, from the dense regions. Okay, and then you ask the user or the expert or whoever to give you the label of these data points. Okay? Now, if you use the uncertainty criterion, then you will look actually at the boundary. So you don't care actually about anything far beyond the boundary. Now, if you use the combination, and that's what we propose actually in this research, is to take into account the dense region, that's basically the clustering, and classification, looking actually at the data points that lie at the boundary. Okay? Skip this, no need. So that's basically just the algorithm. So in a stream, you receive data point, you update your clustering model because you don't know actually about the label. So you cluster it, you assign it to some cluster in real time, and then you compute actually the probability to query this data point. Is it worth to query to ask about the label or not? If yes, then you update your classification. So the user tells you, oh, this point should belong to, let's say, class faulty. This data point should belong to class normal. Okay? And then you can use this information to update your classification. If no, then basically you don't do anything. So you don't update your model because you don't know the label. Okay? Further, actually, once you update the classification in case yes, then you need actually to adjust the cluster weight. So here the weight was, the concept of weight was used actually to deal with drift in particular. So here you can see actually, probably I just skip this one. Basically the second one, which is BAL, and YAR. So these were proposed. So the first one is just uncertainty, labeling. The second one is the BAL criteria. And as you see, actually, these two algorithms outperform really the state of the art. I mean, this the only algorithm we could find. Okay, so it's a pretty good performance using by criteria. Sometimes it's better actually to use just one criterion. It's very difficult, however, to decide when to use just one criterion. But the interesting thing is, of course, that we could simulate drift and show actually that the algorithm can cope with drift. Now, I'm going probably to, we propose another algorithm which deals actually with evolution as well. So while you are training, there is emerging concept, you call it evolution. That's what I mentioned at the beginning, it's about novelty. And you would like actually to, to detect, first of all, concept drift and to detect this novelty. And then you need actually to, ask the user to label data points that are either drifting from the original space or are forming a new concept, okay? And here also we use basically the decision-based active learning, which means we used the approximation to minimize the expected future error. So I'm going to skip this. Again here, you may see actually that we could also have very good results, yeah, using actually, the same concept, decision-based active learning, but in this case, we had to cope actually with concept drift and evolution. To the best of to our knowledge, there is no active learning actually dealing with evolution in data stream. So that's quite novel as contribution. So this, well, we use actually this for different data sets, and as you can see actually, most of the time actually SAL, which is stream-based active learning, performs very well. So the last can compare actually to the other ones, basically on different data sets. And then information-based active learning, I think I'm going to skip it. Again, here we tried actually to look for data points that basically bring more information gain. So we would like actually to ask about data points, that tune better actually the parameters. Now we use actually this for, as I have noticed, there is one talk on activity recognition, ambient intelligence, I think, sometime later. So we use actually this, this active learning, online active learning in the context of activity recognition. And here we built basically a three-layer architecture. So you have actually sensory input coming from the, basically this is, a person actually wearing a number actually of sensors, trying actually to do a number actually of activities, locomotion, gestures, and so on. So what we did is basically to develop this layered architecture to cope with, high dimensional space, because I don't remember actually how many sensors we had. 113. And the point here is to use basically again online learning. Yeah, trying actually to figure out what the person is doing in real time. So data is coming as a stream from the movement of this person, the activity of this person, and you would like actually to know what the person is doing. Now we use basically active learning because sometimes a human being actually, even if you know that he's eating, probably he is eating in a different way. He is not used really to, let's say, to use whatever thing, yeah, probably sitting in different way, eating very quickly. You know, it's the same activity, but the way you perform it can change. So if you build a system actually where to basically to ask, yeah, the user whether he is performing this activity or that, so that you tune your model, so that your model in the future will be able to recognize those, we don't call them abnormal, but normal activities that deviate from the pattern. Okay, so this is where active learning is relevant. One thing actually here is that for building this system we used CRBM, which operates of course offline, so to do basically feature extraction. So this has been done offline, so we prepared the data offline, and then we stream it to one module which stands actually for the online classifier. Basically, it's semi-supervised. And then we use Bayesian stream based active learning to query about activities that are not recognized by the system. So here, okay. So here actually we did, well, two experiments, mainly two sets of experiments, but I would focus actually on the second one. So as you can see, we have actually a number of subjects, basically 4 subjects, for people actually doing activities, and we tried actually to learn a model for each of these subjects. And what we have actually a number of activities, standing, walking, lying, sitting, and so on and so forth. And we tried actually 3 models. So our model, which is CRBM, and online semi-supervised classification. Then we have decision trees, and then support vector machine. And if you look here, actually, because this is offline, yeah, these are actually the result that we can obtain using standard offline machineries like decision trees and support vector machines. The first table. This is just actually to compare, because we cannot compare actually our algorithm with, with the results of support vector machines and DT in online settings. So we had actually to have them actually trained offline, and then we compared our, which is online algorithm, and you see that is very, very competitive, outperforms actually standard offline learning. So this is just to tell you that although we say sometimes that it is very difficult to, to provide lossless algorithms, in this case, it was really very, very good. I mean, the online algorithm outperforms the offline algorithms. Now I'm going to move to this part quickly. So what we tried actually to do in this Proteus project is, of course, to design scalable online algorithms. So the distribution here, meaning that if you are developing your algorithm for big data platform, then you have to think how to, to make your algorithm very efficient, especially if you have high dimensional space, yeah? Then it is very, very relevant. I mean, if you develop it for whatever platform, you have basic, everything is gone. Okay, sorry about this. So what we suggested actually in the context of this project is, of course, whatever we develop, it has to be scalable. It has to be distributed. So I mentioned already the Lasso-based aggregation algorithm. I don't know if I can start with that one. Yeah, so this is the Lasso that I mentioned before, okay? And we basically developed a distributed architecture for it, yeah? So it's again master-slave architecture. So the worker actually computes some quantities and send them, yeah? Push them actually to the master, and the master actually try to combine them and return actually those quantities back to the local, or if you could say workers, and the cycle goes on. I mean, here the interesting thing about it, so far actually most of the algorithms that are distributed are based on gradient or stochastic gradient descent, and this one doesn't rely on gradient descent. If you remember from the algorithm here, we don't have any gradient descent, so we distribute it and we could actually obtain quite good results. Basically, this is also another algorithm, which is the stochastic variational inference. So what this algorithm is about is you could think about it, probably you know, expectation maximization algorithm, very popular algorithm. So this, you may think about it as generalization of expectation maximization. You try actually to not to compute the posterior of a given data point, but you would like actually to model the posterior as a distribution. We used actually this paradigm as graphical model actually to for the LDA, so Dirichlet allocation. Here's some results. Yeah. You could basically use it for all graphical models, you know, hidden Markov models, Bayesian network, dynamic Bayesian networks, random mean-field. You could use this, you know, stochastic inference or variation inference. You could use it really for different algorithms. It's something very strong, and we would like actually to explore it for you know, for different models. For the time being, we tried actually to use the latent Dirichlet allocation algorithm as an instance, and we developed basically the stochastic version of it, so that we can basically get the online version of VI, so variational inference. And this allows actually to do a lot of things in streaming. Okay, so it's basically a transformation of the variational inference into stochastic one that allow us actually to do online learning. And we implemented actually in distributed way. Well, you have to split basically into, again, the same architecture, which is the star architecture. So you have master and you have a set of slaves. Well, it just actually the master actually basically obtain the gradient from the workers and take the average and then redistribute the gradient back to the slaves, where you have basically parallel version running on different machines that compute what we call the variational parameters, depending on, you know, on the algorithm that you are considering. We found out actually that, you know, so just to pick the first one, TSP is quantity actually we use to compute the performance actually of the distributed version of this online algorithm, which stands actually for the running time of online LDA. So if you run LDA online and you divide by the runtime of the solution that we provided. By the way, this is asynchronous. It means if you have many workers, which means many machines, many parallel version running in parallel, you don't like actually to have any synchronization stage where the master has to wait actually for all machines to send their data, so to update, the model. Here we tried actually to be flexible in updating the model by allowing the asynchronous, asynchronous communication with the master. So the master will not wait for all. Whenever it has a partial gradient from some of the slaves, it updates actually the model and redistribute basically the variational parameters. And as you see here, TSP, if you compare actually the online LDA, just the first graph, you will see actually that the proportion, as we said here, so the running time of online LDA is not distributed against the running time of our algorithm here. You see that the time is increasing because the proportion is increasing because the online LDA takes more time, and therefore the fraction will be higher. Here actually we tried really to play around with different numbers of nodes, and we could see basically that the speed up gained actually from the distribution is quite significant without getting too much into detail. So that's basically the Lasso I mentioned before. So what I want to do now is just to say a few words about some of the issues that pertains actually to the things that I mentioned, namely the online algorithm. So we really need very efficient algorithms for streaming data. When we refer to efficiency, here we are definitely talking about accuracy, because we have this lossless notion, and at the same time to complexity. So the time of processing has to be very low. We also actually, in the context of active learning, sometimes we rely on human being or system really to provide accurate label. And most often actually the data you get actually from experts is not necessarily accurate. So you have actually to cope with this problem, taking the risk actually to filter the data, so whether it's update actually the model in a positive way so that the model will react better, or will do less better, and then you can do what we call unlearning. So you basically try really to learn the data that you use actually to update the model, and then we have basically the problem with the delay we have actually in this project, of course, is that the production of the coil, because they have actually an inspection system that provides actually the output sometimes after 15 minutes. So when the coil is already stored somewhere, you get actually basically the output, the expected output. So how can you build an algorithm that deals actually with delayed labels? They're quite difficult problem. Well, there are solutions for it, but it's not usual actually. You see that the labels come later. So this is also something very interesting in the context of data streaming. And then, of course, you have variables. I mean, we can distinguish two types actually of online or streaming. So you may have horizontal if you want increase in the data. So you have basically data points come, every now and then. But you may also think that you may have new features. So you have new data points, but also new features. How can you build a model that allows you really to do both? So you cope with horizontal growth of the data, but also vertical growth of the data. Very, very tough problem. And at the same time, you would like, of course, I mean, that's the purpose actually of doing actually feature selection online, is basically to try to figure out those features that are very influential as you have more data. So these are quite interesting research questions. We mentioned actually some of the things about it, about drift. We usually rely on some mechanisms to detect drift and then take action. Now, if you know actually a bit of the kind of drift, how can you exploit that? So, to be honest, I haven't yet seen any paper really dealing with this problem. Now, the main issue I mentioned actually when talking about distributed online learning is scalability. I mean, this is very crucial. Now, we have sensors everywhere now, and we would like actually to make use of that data in different applications. And the problem is now how to devise online learning algorithms that are scalable, that can cope with more data, that can run also on many machines, on big data platforms. And I showed actually some of the examples, Lasso and the stochastic variational inference, how we do that, actually by building local models on the slave level, and then combine them at the master level, and then communicate back actually the actual model to the slaves, and you cycle over this. But as we said, actually the most standard way actually for doing this is stochastic gradient descent. We tried actually with Lasso, which doesn't actually rely on stochastic gradient descent, and I think that's a good contribution. So just actually to close this, so we are basically running Proteus project, Horizon 2020 project, which is about devising scalable online machine learning for data streams. So the project involves a number actually of partners. And we would like actually to develop a library called Solma. We'll come to this. So this is what we want to do. So you have the Flink actually, the big data ecosystem, and probably some of you, or probably many of you knows Flink. So this is actually a European big data platform. So what we want to do is basically to build a machine learning library, so scalable online machine learning algorithms for Flink. So that's basically the main idea of the project. Now, Flink right now is a hybrid architecture. It's not yet mature, so we are still developing different actually modules to accommodate streaming. Basically, could say some words. So, what the consortium has been developing over last year is basically the Proteus engine, how to accommodate basically machine learning algorithms, how to process streams of data. To be honest, we haven't yet pushed too many algorithms in the GitHub because my people, most of them are familiar with R, with MATLAB, and so on, and this requires actually Java and Scala and so on. So we are trying actually to populate the library as soon as possible. So that's basically what I wanted to say. I think that's the. Yeah, I think that's it. Thank you very much for your attention. Thank you again, also for giving me the chance actually.
Well, thank you, Hamid. It's an impressive work, that the one that you have shown us. Is there any question? No, I have many, but I only made one. Now, you said that at the same time, you have the problem of having to select the features that are important regarding the budget. So have you tried a balance between cost and the importance of the feature, for example?
No, we didn't do any work, to be honest, in this context of feature selection. What we did actually is Lasso algorithm, which, the selection of the features is embedded within the algorithm. So we didn't do any addition to that aspect.
Yeah, it was a nice algorithm.
Yeah.